Hi, everyone. I'm Chen. I lead the perception team at Waymo. In the past year, Waymo has made a significant progress in terms of the number of trips that we serve. Today, I want to talk about a few really important problem areas while we're scaling the product significantly in the past couple of years. Today, for nominal driving, there's really not that much challenge anymore. So today's system for nominal driving, the system generalized really well if you go to different geographical locations, and even if you move the system to a different vehicle platform, it is really a lot of the long tails and that matter in today's situation. And that's why I want to talk about those problems, which can be lesser known, because Waymo pretty much is the only AV company who have such a large scale of development. And I would also want to encourage you to work on the harder problems, because those are what that matter to an actual product. Okay, just a very short intro about the scale that we operate. It's a very short video. Today, we have about 250,000 trips per week. That's about 1 million trips every month. To make sense of the scale, last year, 2024, the whole year, we have served about over 4 million trips for the whole year. And now we are already at 1 million trips per month and still accelerating. So we're in a pretty fast pace of increasing the scale of the product. Going to the next one. Okay, great. So in SF and Phoenix and LA, right now there's no wait list. So you can go there and download the app and take the ride. This is a pretty convenient. That also brought a lot of visibility to the product, because anybody who drop by those cities can experience the AV rides. In Austin, we partner with Uber. So if you hail a car from Uber app, sometimes you'll get a Waymo car. You can also select that you want to prefer Waymo car, so you have a higher chance of getting it. Expanding in Silicon Valley as well. And also Atlanta, we also partner with Uber, and that will open to the public users soon as well. And next year, 2026, we're going to bring Waymo One to Miami and DC. And here's a map showing all of the cities we are operating and going to open operation, and all of the cities we've tested, including the 10 road trip cities this year, and also Tokyo. We've had a few cars arrive at Tokyo, start doing data collection there already. So Waymo's mission is to build the world's most trusted driver. What does that mean? So given 1 million trips every month, basically our cars see all kinds of situation every day, every week, every month. The scale is very large. So it takes a strong commitment to both the technology and also the whole product to make sure at this scale, the product really bring a safe experience and bring also a comfortable user experience. So user want to come back and take the car again. To give you some examples, this is a compilation of a recent events. In the first one, you can see the motorcyclist bumped into the middle of the road and fell, and we needed to respond to it very quickly. The second one is a cyclist rushing through the slope, and we detected and stopped in time. Also, red light runner. This one is a scooter, fell. I think there are a couple more. This one is a car crash right in front of us. This is a nightlight, a red light runner, where we detected early enough and stopped and nudged right in time to avoid it. Okay, so this is a recent safety research paper that's published in a journal, where by looking at over 56 million miles that Waymo driver has driven, the Waymo driver managed to drastically reduce the amount of crashes involve severe injury, including pedestrian, cyclists, and motorcyclists. And to achieve safety, it is not just about the software. It's not just about the model, the system running on the car. The hardware system also have a, carefully thought through redundancy built into the whole system. For example, redundant power systems, braking, steering, compute. All these matter because at a large scale, you have to make sure the hardware faults are not causing a big trouble to the product. And a lot of the times for transient hardware failures, we also have the ability to recover so that the car can still move forward without being too much impacted by these transient failures. And of course, the strongest momentum to push EV technology forward has been the advancement of ML. And starting from the very early days, we started using the deep net and also continuously using SOTA technology, and the onboard stack changes very rapidly all the time. So in order to scale to different geographic locations, different platforms, sensor suite, and compute, we build a Waymo foundation model and distill it onto onboard systems. And through doing this, we can have more generalization power from the foundation model, but also being able to quickly adapt to an onboard system that can deploy into different platforms. And this foundation model encodes all of the sensor data, including all of the cameras, radar, and LiDAR, and also have a world knowledge built in and decodes all of the driving relevant tasks, including perception behavior simulation. I think this you are familiar with. But what I want to say is that just having a foundation model doesn't mean that it can readily solve all of the problems that we need to solve. Foundation models it has a great generalization power, but for us, the way for it to be really useful is not only does it generalize, but also it should come out of the box, solve most of the long tail issues that we care about. Otherwise, you wouldn't be able to leverage the model and distill into a powerful student models. But also during the distillation process, it is very critical that we can keep all of the generalization while you go from a large teacher model to a smaller student model, and better yet, keep all of the zero-shot capability, which is also not easy to achieve. In addition to that, when we produce the student model on the car, it really have to fine-tune and solve all of the data slices what we care about, solve all of the long tails we care about. That's a very high requirement there too. So in the rest of the talk, I will quickly go through a few problem areas to give you a sense of what are the problems. First one is weather. Since around mid of 2003, we had zero weather-related downtime in SF and Phoenix. That is pretty hard to achieve. That means basically we can drive through all of the dense fog situations in SF and also the monsoon in Phoenix. I have a video here for the monsoon. It is a very heavy rain and heavy wind, and you can see there was a pedestrian walking on the sidewalk, which is not recommended. So we are able to differentiate what are the weather situation and recognize all the objects correctly. As you approach, and you can see the wind is getting really strong. And we have been operating this situation for over 2 years now. Next one. So so one thing is you have to drive through rain, but also after rain finishes, there's all kinds of road conditions that we also handle. So this is one example with a puddle. So when there's a puddle, we detect where the puddle is, the size of the puddle, and in this case, we decide to lane shift to the left to avoid the puddle. But there's also flood, which doesn't happen all the time. We've only seen only a few hundred of them, which is way less frequent compared to many other phenomena that we see. So this is a pretty long tail. And however, the requirement on both precision and recall are very high. Let's say if we have false positive flood, then it can really impact where you route and whether you get stuck in such situations with a false positive. However, if you have false negative, then it's not great to drive through a flood. It can be pretty scary. And we've seen it in all the geographical locations, especially this season. There are a lot of rain in all the cities. And when we look at flood, it's not enough to just see, oh, there's water. There's also the depths of the water. So it requires a lot of context information to know if there's a flood or it is a puddle. So we use VLM so that really we need to leverage the world knowledge so that we can handle this situation with a few shot learning. So here's one simple example with a parking lot with a standing water and not super deep flood, and we're able to detect there's a flood and do a multi-point turn and exited the parking lot from the other direction. So snow, we're working on snow. So it is very interesting because it's also pretty demanding on the vehicle hardware as well. These are a few examples from the data collection that we did this year from Truckee. It's the Lake Tahoe area. And the snow accumulates pretty quickly on the car, so it can block all the sensors very quickly. So for the sensors, there are both heating and also cleaning, so that at least you can see. Here shows a video of the wiper on the cameras, which is pretty cute. And you also need to be prepared that the sensors can get fouled anytime. Here are the two examples from below. And whenever sensor get blocked, we need to clean it, detect it and clean it quickly. And also the models and the system need to still operate while the sensors are fouled. And this is an example where we drove in a snow condition. See, this is in Detroit, and there are some snows in the air. The road condition is not too bad, and the cameras are fouled, as you can see. But this this level of fouling is not too much a issue for the system. But still working on it, especially for heavier snow conditions. So with this one, I want to show that one of the big challenge of solving snow is where do you drive? Does map still matter? And even if we know the map, in these conditions, the other drivers don't know the map. So you really have to just understand the situation and look at the other agents and decide how to drive. Sometimes there are tracks on the road. You want to decide to follow it and not follow it. And when there are buildups on the snow on the road, also we need to understand, is the buildup really deep? If I drive through, will it cause damage to the car? And also estimate the friction so that we can give the right signal to the motion control. And sensor fusion. So this is an example of video where it's a high-speed road. There were two pedestrians climbing over the barrier from the left side. I've seen this video many times. I still cannot see the pedestrian in the camera image. But you can try here. But I have another slide just to highlight where they are from the camera. So it's an overlay of the object on top of the camera image. It's very hard to see those pedestrians. I have another similar example on freeway as well. You want to watch on the right side. From the top, you can see there's a white box showing the location of a car, and you can try to see if you can see it from the camera image. It's also extremely difficult. So I have another slide just to highlight. There's a car over there on the shoulder, completely dark. Another example, this is a dust storm in Phoenix. Phoenix have monsoon, also have Haboob. When Haboob happens, you have a lot of dust. And if you look at LiDAR, you can clearly see a pedestrian on the right side. And this is important because this pedestrian is pretty nearby, and we will need to leverage different sensor modality to be safe in those situations. And I want to talk about occlusion, and this is a very critical problem, and we see it all the time. Think about when you drive, there could be agents coming from invisible areas, occluded areas at any time. And this is very important because even anticipating where agents will come out from occlusion will help us drive safely and also respond fast. I'll show you some examples. This is a bus, and there will be a cyclist coming from behind the bus. Here's another one, and there's a person running out from the building, and we detected and stopped, heartbreaked. Here's a similar one. There will be a cyclist, a child cyclist coming from the left side. These are often also pretty common. So occlusion reasoning means that we want to reason about object existence and also states in the regions where we cannot see them. And it is critical to driving safety. As I talk about, they are very, very common, and we need to be able to anticipate and respond fast. But these events, this problem also is very low likelihood and can be very high severity. For example, in the occluded maneuvers, while we are trying to make an unprotected turn, there could be a speeding vehicle coming out from behind another vehicle. And when we drive around large trucks or buses, very often there could be cars and cyclists or even pedestrians behind them. And similarly for occluded pedestrians. And this problem is very hard because one is that it is not well defined. It is not something you can infer from sensor observation. In fact, it's the opposite. It's when you infer something without a sensor information. And also it's not deterministic because it's a likelihood. It doesn't always exist. An object doesn't always exist. If you want to create a benchmark for occlusion, it's hard because you don't have a ground truth. You don't know. Even if there's no object, we still want to know there might be so that we can still behave in the right way. It's subjective because some, even for human drivers, some of them are more conservative, some of them are not. And there's a diversity in the agent. There are cars, pet, and cyclists, because for each of them, they can show up in different places, and also we have different state estimation for the potential occluded object. Highly contextual. I've shown a few examples depending on the time of the day, the scene, and the location, and the prior for where object could exist is also different. So fundamentally, we want to have a probability estimate on the occluded agent based on what we observe and based on what the sensor valve is. So the first step is that you want to estimate object prior. And how do we do that? One part of the object prior comes from learning all of the statistics from the driving data. So you can learn in this situation, that situation, what is the likelihood that I have seen an object. However, the really useful one is that you can also use slide sensor cues to really boost your prior. So that will really help you react fast for such situations. And the second step is that we also use sensor valve to eliminate the obviously not feasible ones. So not only object existence, knowing the speed prior is also very important. I want to show this video. This one, there will be a red light runner from the left, and we detected early and stopped, but the other car, hit with this car. For this one, the way it's relevant to occlusion is before the speeder shows up, it's actually occluded by two other vehicles on the left side. So we don't, from sensor data, it's hard to see the speeding car early enough. But because of the occlusion, we always know that very likely there could be a car behind it. But here the key is, what is the speed prior that you give? If you give a very low speed prior, then you might be moving forward too much and get to a position that's unavoidable with a collision. But if you give the speed prior too high, then we're never able to make progress in any intersections. So there's also a lot of care into estimating the speed prior for different situations. And scene understanding. I want to show you a few scenarios where the overall scene understanding matter a lot. So a typical one is a construction. This is a simple construction scenario where we recognize the sign. It shows a slow, not stop. So we move forward and reason about the geometry of the driving. There's a cone, so we should move to the other side of the road and move forward. It's a simple construction. And there are some cases where the scene understanding is not static. For this one, it really depends on the gesture. So at the beginning, we were stopped there because the traffic officer had a stop gesture for us. And after the traffic officer stopped the other vehicle, he did signal us to go left. That's when we start moving. So this means that you have to respond to some signals that are more dynamic. See, these are really cool. These are the active incident scene cases where there could be an accident. There are a lot of EVs, and we need to reason about the scene and do the right thing. Here's the one where we know the right lane is blocked, the straight lane is also blocked, and we were waiting for the other fire truck to exit, to finish the turn. And after that, we decided to turn left. And there's another one. Okay, this one is on freeway. There's a accident to the left side. There are many EVs actually. So pretty early on, we understood that the left part will be blocked. So we did two right lane shifts. Here's one, and we did another one to move to the rightmost lane and started to merge with the rest of the traffic like this. And as we drive along further, you will be able to see to the left side, there's a car crash and many police vehicles and many officers over there. And we continue to merge with the rest of the traffic and move through the scene pretty smoothly. So in those type of things, the question here is how do you solve them? So usually you see all kinds of objects and attributes. Even caution tapes, believe me, is a very critical object type to recognize. So the question is, if you recognize all of those, is it sufficient? It's not sufficient because then you still need to make sense of what type of scene that is and also make sense of the geometry and also understand, should I interact with with an officer or I'm confident with the geometry, I should just go. So all these come into the totality of solving this problem. And obviously here, the object representation is not sufficient. And the question is, what kind of representation you want to build to solve this problem? Or should you do end-to-end driving, just understand the scene as a whole and decide where to drive? Uh, Next, I want to show a few slides about the data. Data is very important. And, we drive millions and millions of data, accumulate all the miles very quickly. It is very important to have a large amount of data, but you also don't want to just use all of them because then your training becomes inefficient and you're not focused on learning the right problems. So it is very important to select the most relevant data. So we put in a lot of effort into making our data curation system really well. So we have a list of different technologies, including language search, embedding-based search that works for both appearance and also behaviors, few shot learning on the fly while you search, and active learning, and many more. To show you some examples on the image side, here's some examples that are very typical, all pretty relevant to driving, and they are debris, fireworks, fire hazard, and different type of VRUs cases that we care about. We also have the video search capability. These are also very critical because some of the events you need to know the video to make sense what the event is. Here you see a car collision. These are all from our real driving data. Car collision, car drifting, and wheelies. And wheelies is very common as well. And For the product scale, a depot is one part most people don't know about, but I think it's very cool and it can give you a lot of efficiency. I want to show a couple videos to illustrate the idea. This is a picture of the Tolan depot in SF, where you see the cars are charging. And so the way it works is when a car goes past to a depot, you see on the dome, it shows the car and what kind of operation it needs. It'll drive to the station for charging or for ops to take a look. In this case, the car drives automatically to a charging station. And right now, we still need a human to plug in and plug out. We don't have a robot. So that shows it. And after car is charged, it'll just go out automatically by itself to serve more users. And recently we built up a factory in Mesa. So this one, the cool part of it is after the car is assembled with all the sensors and also the compute, it goes through a list of checks automatically, and then it drives out by itself to serve the user. So from driving out to serving user, it takes as little as 30 minutes directly out from the factory line. Last but not least, I want to show two really interesting videos that shows fast real-time decisions. And the first one is you can see the car cuts through. What's interesting about this is, if you look very closely, we first decided to nudge right and also honked at the car. And then quickly we decided to go to left because the car didn't really yield. So that's the, really fast decision-making over there. Here's another one. You want to watch for the black cars to the right side. There's one car overtaking the other one, causing it to hard brake. And then afterwards, a hard brake again, and we dodged it, like at really close distance. There are actually many examples like this. Let me show you again. This one. Look at the black car to the right. Yeah. And that's all. And if you're excited by these hard problems, please come talk to us. And there are actually many other hard problems that we need to solve. And many of those can also benefit from a technology improvement and also, all the evaluation, everything simulation so that we can solve them even faster. Yeah, and thank you.